Welcome to the satellite communication course. So we have seen earlier that a high power amplifier, the requirement for the high power amplifier is a EIRP, effective isotropic radiated power. So to achieve the EIRP, we require the power to be transmitted is to be high and the gain is to be high. So generation of a power, so you can use a high power amplifier or generating or getting the large gain of an antenna. Gain, it is depending upon that size of an antenna or what type of an antenna we are using. So in the case of a high power amplifier, we can use a tube, we can use a TWTA, or we can use a solid state power amplifier. So in the case of a solid state power amplifier, so if the electron mobility is high, then we will get that a maximum output power. So in a SSPA. So similarly, the same concept is there because a low noise amplifier, if it is designed using a gallium arsenide fade, so if we use again the same technique, if it has a high electron mobility, then this LNA can be used as a good receiver. Okay, that is about a amplification is good at a receiver there. So now to improve the electron mobility, so we need to provide a junction across this component or across this device that will be heterojunction, and because of that heterojunction, electron mobility will be higher here. Now we'll see that in next part, once a transmitted signal reach here, then we need to know about how that signal is to be up converted. So generally that IF signal for the C band amplifier or sorry C band transponder, that can be of what we can say, it has a 36 megahertz of a bandwidth supposed to be, if we consider that, or we can say that it has a center frequency of a 70 megahertz suppose. So then we supposed to be consider that the spectrum of a IF or a modulation of a IF carrier, that is supposed to be in this 36 megahertz of a band. So for example, if we consider that there are three different modulated carrier, you can say that a 59 megahertz, suppose 70 megahertz, and we supposed to be consider that is about 8 to 82 megahertz, and it has a bandwidth of what, 8, 8, and a 10. These are the bandwidths for this particular modulated carrier. Then for the transponder bandwidth of a 36 megahertz, so then how this spectrum or how this modulation of that carrier in IF band will looks like. So we supposed to be draw here 70 megahertz now. We supposed to be consider. We have a 70 plus 4, 74, 70 minus 4. We can say that it is to be a 66 here. We supposed to be consider that another band is about a 59 now. 59 plus 4, we say 63, 59 minus 4, that will be of 55. Another carrier is about, we say it is about 82. So 82 plus 5, that is 87. 82 minus 5, that is about a 77. Now this one is about what? We have a modulation carrier in a IF band. Okay, that is about, we can say that modulation carrier in IF band. Okay. Now supposed to be this signal is to be up converted. Now how this signal is to be up converted there? So that we'll get that a specific frequency band is about the 36 megahertz. So now suppose this one is about, we can say that 52, and this one is about 82 here. So this band is about a 36 megahertz of a band. So means we raise this 59, 70 megahertz or 82 megahertz, that is about the center frequency of that particular modulated carrier, to uplink the signal or upconvert the particular signal. So if you supposed to be consider that a up frequency for this is about a 6718. So in that case, a 6718, we have the a same bandwidth is about a 36 megahertz. Then whichever the IF signal is there, that is to be multiplexed with the your signal. So we will get that a mixer output. That mixer output is nothing but what? We have the 6718 here, one band, another band for this 82 megahertz here, likewise. This one is here, that is about a 6730, and another band at this 59 here, we'll get that 6707. 6718 plus 70. Okay, 67. So this one 70 plus 6718. So we have a 6788 megahertz here. Okay, 6718 plus 70, we'll get that 6788 megahertz. So if you apply, sorry, if we apply the a local oscillator frequency of a 6788 here to this, so 6788 plus 70 or 6788 minus 70 means we'll get the two component, that is sum component and a difference component. So in that case, so we can select that 6788 minus 70, so that is about a 6718, that is the difference component. So according to that, we can find out this particular frequency component. So here the uplink frequency signal supposed to be a 6788, means this is about a local oscillator frequency, and that local oscillator frequency we use a crystal to obtain that a local oscillator frequency. Now what will be the circuit here for this a 36 megahertz of a band? This is about a 36, total band is about a 36 megahertz. So in that case, if we use to get this particular 6718 megahertz of RF band output here for this particular signal, then what we require? We require the input from the modulator That input from the modulator is what? F of IF, that will be of a 70 megahertz. This one, 70 megahertz. Okay, it's about a 70 megahertz. And then that input is given to the mixer. This one is about a mixer. Then we have the a frequency multiplier, because we need to get that output is about, for this local oscillator, that will be what? A 6788 megahertz is the output. Then we will use a band pass filter, and then output of this is given to the RF amplifier, and we'll get that a IF RF, that will be of 6718 megahertz. This one is about a 6718 megahertz for the given particular signal. So frequency multiplier, we will provide the input to from the crystal oscillator, because that much frequency not generated by the oscillator there. So the crystal oscillator, output of this crystal oscillator given to the frequency multiplier. So we'll get that a up conversion. So now this up conversion, it is about only a single stage. Means we have the input, we have the local oscillator output, we are mixing, we'll get that a output of a 6718. But again, instead of a single up conversion, so we can use a double conversion here. For the double conversion, we supposed to be give that input FIF is about a 70 megahertz from the modulator. Then here we have a mixer. Then we can say that we require a frequency multiplier, or we can say that a PLL here. We can say that crystal oscillator, and that input we are providing. So here we have the local oscillator output is about a 700 megahertz now. So 700 plus 70 or 700 minus 70. Because generally we supposed to be consider that a mixer output is a sum and difference component. So we use here supposed to be a difference component. This one is about your amplifier, and then again we use a mixer, and then we have the FLO, that is 5948. 5948 plus 700 plus 70 and 700 minus 70. So two output. So in that case, we supposed to be consider 700 minus 70 means what? A 630 megahertz. That is about this. So that's 630 here plus 5948. Then we have a band pass filter here, and then we have RF amplifier, and we'll get that a RF output, that is about a 6718 megahertz. Mean here we are using a double conversion. So means we are using a double conversion frequency synthesizer here, and we have the reference oscillator. That is from this crystal oscillator. Okay, reference oscillator. So means we are using a double conversion. Means up conversion, either we can use a single conversion or we can use a double conversion there. So similarly, for the down converter, because Up conversion means what? It is for the uplink signal. Similarly, for the down conversion, so we need to use again a single conversion or a down conversion. So now I supposed to be draw here a double conversion down converter instead of a single conversion there. I'm just supposed to be consider double conversion because FRF, that is coming, that is a downlink signal. It has a 4 gigahertz of a downlink signal. Then supposed to be we use a mixer one here. We have a band pass filter. Then again we have the IF amplifier. Output of this IF amplifier, again it is going to the mixer. Then we have a band pass filter. Then we have the IF amplifier, and then we'll get the output that is about a 70 megahertz. Now again here we supposed to be consider that a PLL multiplier. Then we supposed to be consider that a crystal oscillator. Here we can supposed to be consider that a frequency synthesizer. Here we consider that reference oscillator. So now if you see that this is about a 3 gigahertz. Okay, so means sum and difference component. So here output will be of a 1 gigahertz. That is supposed to be passed on the 1 gigahertz of a signal. Here you see that it will reach 1 gigahertz signal here. Then we have the local oscillator that will be of a 930 megahertz, 930 and 1. Okay, difference component here is about a 70 megahertz. So that's why we'll get that output is about a 70 megahertz. So we can consider here for the down conversion either single stage or a multi stage there. So now this is about a component of, we can say that, up conversion or a down conversion. So we supposed to be consider that a given particular mixer here for the down conversion or up conversion, whichever the mixers we are using, whether we supposed to be consider that some component or a difference component there. So according to that, we supposed to be choose that particular filter here, because since it is not able to generate that 3 gigahertz of frequency, so that's why we can use a multiplier here and that frequency synthesizer and reference oscillator from this local oscillator there. Another component of a earth station is what? The IF equipment. So generally that IF equipment, if you see that it has a modulator and a band pass filter, because a modulator means that modulating whatever the terrestrial interface circuit here. You can say that from terrestrial systems. So we can say that FM modulator, okay. Then we have the PSK modulator. Then we have the TV oblique FM modulator. Then we supposed to be say that we have the SCPC modulator. a single channel per carrier modulator. Then for every input, so we supposed to be use the band pass filter. Okay, because that band pass filter that will restricting the signal here. So here is the band pass filter. This one is about the input. And then all these IF signal that are combined here. So that's why we can say that IF patch panel, or we supposed to be say that we have the combiner, IF combiner. Okay, all the inputs are combined, and then that will be output through this FDM transmitter here to the up converter. So now this one is about for the transmitting side. For the receiving side, you just say that we have the FM demodulator, then PSK demodulator, then we have say that TV oblique FM demodulator, then we can say that SCPC demodulator. Then for separate band pass filter, then all these whichever the IF we have. So here we have the IF patch panel that will be divider. Since we are getting the output from this FDM RX, that is a down converted signal, and then that will be the input to the to terrestrial system. So just like if you consider that, so these are the different modulators we supposed to be used. If we have the analog signal, then FM modulator and demodulators are used. If we have a digital signal, then we can consider that a PSK modulator and demodulator we can use. So if we have the a FDMA system, so in that case FM or a PSK modulators are used. So according to that, what will be your input? So we can use that particular modulator for the given particular input there. And then we supposed to be consider that after modulator or demodulator, we supposed to be use here a band pass filter, because that specific spectral band for the transmission or for the reception, it is to be used. So that's why for the specific band, we supposed to be consider that the equalizer here with this respect to the particular filter there. So that is about a IF system component. And if supposed to be you consider that a baseband equipment, so in the baseband equipment, we have the a terrestrial input, or we can say that a various input from the terrestrial system. So suppose we consider that a analog voice channel, that is about the input. So this one is about TIF, terrestrial interface we supposed to be say. We have another TIF here. Then we have a voice coder here, and then the various TIF, voice coder, and that will be input to the digital SCPC modulator. Okay, means we have a terrestrial interface model from this various channel that will be input to the SCPC modulator. Then we supposed to be consider that a PCM channels, again we have a TIF, terrestrial interface model for this PCM channels, and for this particular terrestrial interface channel, so we are using a time division multiplexer there, TDM, and then that will be transmitted to the QPSK modulator. Then we have the analog voice channels, then a TIF, terrestrial interface model, terrestrial interface model. Then we supposed to be consider that frequency division multiplexing or a multiplexer here. So then that will be input to the FM modulator. Now that is about a baseband equipment. This is when for the transmit. Then at the receiving, so then instead of a 2, we can say that if from SCPC demodulator. Then reverse here. Okay, the input will be reverse. That will be a, instead of a coder, it will be a decoder, voice decoder, then terrestrial interface, and then to the analog voice channel. Similarly, for the QPSK modulator, instead of that, we can say that from demodulator, likewise, then we have a time division multiplexer, then we have a TIF, and we'll say the PCM. Similarly, here, instead of a FM modulator, so from FM demodulator, you can say that from FM demodulator input here, FDM, then TIF, and analog voice channel. So these are about what we can say that a baseband equipment, it has a PCM channel or a TDM channel. So if you supposed to be consider that we have the analog voice transmission that is to be sent from the earth station to the satellite, then if it is a few voice channels are there, we can use a SCPC mode, or we can say that individual users can use a voice channel, so we can say that they can be used in a SCPC mode. So then we can say that analog or digital, so according to that we can use a analog SCPC or a digital SCPC, likewise that signal is to be used there. So in case of a multi-channel there, so we supposed to be use a TDM or a FDM here. So in that case, for the analog voice channel, we say it is about a FDM system, FDM supergroup there that can be used for the transmitting there. For the PCM channel, so we can use a PCM TDM system for the transmitting the data that is in a digital form. When it's about analog data here. That is from the earth station we transmit the data and receive the data from the satellite. So that's why from demodulator. Okay. Then one more important factors for the earth station performance So that is performance of a earth station. It is totally depending upon that what will be power transmitted and what will be the power received. We generally we say that whichever the earth station we have, so in that case it will transmit some particular power. So in that case we need to know about that what will be the EIRP for the transmit there for the transmitter, and how much will be the lower power will be received by this earth station. So we'll talk about the transmitted power first. We say that EIRP. Then in that case, what will be the power transmitted from this earth station? So we know that it transmitted power of a amplifier, high power amplifier, and a gain of the transmitting antenna. Gain of transmitting antenna. Okay, TX antenna. So we can say that EIRP here, because at the transmitting, how much is the maximum power can be transmitted by the earth station there. And that gain of an antenna, if you consider here, we say that it is about 4 pi by lambda square. So in this case, that A is nothing but what? The aperture area of an antenna. So means area of an antenna increases, the gain of an antenna is increases. So we supposed to be consider that a power amplifier output that is to be connected to the antenna through the waveguide here. Because if we are not connecting through the waveguide, there may be a loss. So that's why we need to use, or we need to feed the antenna using the proper waveguide. So then we can minimize the loss there. But again, if we use the waveguide, then again there will be a loss, and that loss is called as a waveguide loss. So that's why EIRP, we say that transmitting power as well as the gain as well as the what will be the loss through the waveguide there. So if you express in terms of a dB here, so EIRP, it is in terms of a dB, that will be what? Transmitted power in terms of a dB plus gain in terms of a dB minus waveguide loss in terms of a dB. That is about a output. It is in a dB watt. So that is about a total output. Here we can say that a watt. So that's where it is saying we can say that a dB watt. So that is about a transmitting side. But in the receiving side, what will be the G by T ratio? So receiving side, this one is about a earth station transmitting side, performance of a earth station at a transmitting side. But at the receiving side, we need to measure the gain of an antenna and a receive noise temperature. This one is about receive noise temperature, and this one is about a gain here. So gain of the antenna, generally we say that it is depending upon that a size of an antenna. And again, if you consider that a T, that is about a noise temperature. So that's why that G by T ratio for the receiving antenna, it is depending upon that a noise temperature. So gain, it is the operating temperature as well as the size, and this noise temperature, it is the effective noise temperature that will be applied to the, or it can be seen from the amplifier there. So means at the input side, the temperature of an antenna as well as the temperature of the amplifier. So that effective temperature we supposed to be consider that the overall temperature from this both the component, and then we can find out that a G by T ratio. So that is about a G by T ratio for what, a receiving side of an antenna there. So we say that a performance of an antenna, it is depending upon from the transmitting side as well as from the receiving side. Then another factor is about a redundancy and a reliability. No, that is about a word reliability. So that component, how long that component use. So it's supposed to be satellite there. So we could not replace any component there. So that's why we need to use the component, or that component can be used for the longer duration there for 10 years or 15 years. So in that case, so we can talk about the reliability. But if we consider those components for that will work for the long duration, so in that case, to achieve that particular reliability, so then the cost of the system will be increased here. So we you need to use a high reliable component. So that's why the cost will be used increased. And redundancy means what? So some components in a subsystem, some redundant components to be used in the subsystem, again it will increase the cost there. But in the case of a satellite, so we could not tolerate that reliability here. So in the satellite communication or in the satellite there, so cost of the component can be increased because we require the high reliability in the component there. But in the case of a earth station, so that we have the various components present in the earth station, or individual component can be replaced there. So in that case, if you consider the design of a earth station and a satellite there, so reliability and a redundancy in that factor here, so that will be balanced for both the earth station and the a satellite there. So because we can perform a large earth station, and that large earth station carrying the large traffic, then in that case a reliability will be critical for the large earth station. Okay, we can say that reliability because of the large earth station, large traffic, so reliability will be a critical thing. So we say, consider that for improving the, we can say that for improving the reliability there, so we need to improve the, or we need to provide the redundancy in the critical subcomponent. So that's why we can improve the, we can say that improve that reliability using the redundancy in the critical subcomponent, because some components are fail while working. So because of that particular failure, so then what happened, So your system will goes off there. So in that case, instead of that, so we can say that if some critical component can be used, or that can be if a standby, or we can say that some system component can be repaired or it can be replaced there. So in that case, we can improve the redundancy there at a earth station. So for a given earth station, what will be the failure rate? So how you can we can say that your system components are failed there. So we need to talk about that a failure rate in the given particular system there. So if it is a larger station, because of that large data is there, so there may be a large failure rate. We have a smaller station, so should not be any redundancy. We can replace it. But for the larger station, so reliability can be improved by using the redundancy there. So low Earth station cannot afford that particular reliability there, means redundancy there. So that's why we can say that whichever the subsystem components are failed, so that can be replaced if they fail there. So we can afford easily for the low Earth station. But in the case of a large Earth station, so use we can go for the redundancy to improve the reliability there. So then we need to find out that whichever the components are able to repair there, if supposed to be it is a smaller station or a larger station. So we need to find out what will be the mean time required to repair the component there. So that is about a mean time to repair for the earth station, rather than that a mean time to failure. So if you see that your system will be available, so availability of a system, it is depending upon that mean time between failure and mean time between failure plus mean time to failure. In a satellite communication, if supposed to be some systems components are not used, or it is not to be replaced there, so then that satellite can be replaced or satellite can be removed there from the specific place there. So that's why the life of the satellite is low, because they have the lowest standby component present in the satellite. If supposed to be some transponder is not work, so that transponder is to be replaced directly. But in the earth station, we can easily replace the each and every component one by one. So that is about your redundancy and reliability. We can find out that from this, what will be the availability of the earth station for a given particular period of a time. So you should know that what will be the mean time to failure, or what will be the mean time between the failure. Okay, that is about the redundancy and reliability there. So we have seen today the baseband equipment. We have seen that earth station performance. We have seen that the IF equipment. We have seen the up converter and the down converter here. And now we will see that emission control facility there. Now in the supposed to be in a up conversion or a down conversion, mostly people are using a double conversion technique to improve the performance of the system. That's all for this session now.